So my name is Ines Iraki. I was mentored by Khalil Bisroor, and today I'm going to talk to you about the mathematics behind Bitcoin or most cryptocurrencies, understanding elliptic curves and how they work. First of all, what's an elliptic curve? An elliptic curve is something that looks a little bit like this, and its expression is y power of 2 equals x power of 3 plus a times x plus b, and let's consider for now that a and b are real numbers, okay? It has a little bit of specificities. For example, it's always symmetrical around the x-axis, so it's always the same for all elliptic curves. And another specificity is that if you draw a line on an elliptic curve, it can touch a maximum of 3 points, never more than that. Pretty easy for now, right? So here are some examples of elliptic curves. Right here, where there we have y power of 2 equals x power of 3 minus 1. And in general, an elliptic curve either look like on the top, like it's one line, or on the second line, where it's like two different parts. For most elliptic curves, it looks like this, okay? One thing that is important to define on an elliptic curve is the point addition. So how can I add, for example, 2 points? Let's say, for example, I take point A and B, and I want to know what is A plus B, like where would that be on the curve? That's pretty easy. You just have to draw a line, see where the intersection is right there, reflect it on the other side, and right here, you'll have your point C, A plus B. Pretty easy, right? What we do usually is that we define a base point, 1 point, and we keep on adding it to itself. So how do you do that? You just have to draw a tangent, see where the intersection is, reflect it, and right here you'll have 2p, p plus p, 2p. Now, for example, let's say you want to get 10p. How much is 10p, right? It's pretty easy. We have a rule that says np plus rp equals n plus r times p. So how do we do that? We already have the 2p right there. So let's say p plus p, 2p. Then you take 2p, 2p, 4p, 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 8p. You already have a 2p there, so 8p, 2p, 10p. Let's do it on the graph to see how it goes, right? So we have this point right here. I want to add it to itself like we did it previously. So I'm just going to draw a tangent from this point, reflect it on the other side, and right here I'll have my 4p. Now, to follow this step, I want to add this point to itself again. So what I do, I just draw a tangent, go there, reflect it, and right there I have 4p plus 4p, 8p. Now that I have all the points that I need, what I just do is just the first step, and add 2 points together. So I'm going to take my 8p right here and my 2p right here. I'm going to draw a line, see the intersection. So I have one right here where I draw a line. As I said, at first, it can touch a maximum of 3 points, so you won't have any confusion. The third point will be the addition of the 2. And right here, the intersection, you reflect it on the other side, and you'll have your 10p. Pretty easy, right? Okay, perfect. So this that we just explained, it's possible because they form a group structure. And we define the addition of the point in R, okay? But it's also applicable to finite field. And this is where it's going to be interesting, and from now on we're going to focus on how it goes in finite field. It's a little bit more complicated there, but it's the same concept that extends to that field, okay? So I'm going to take an example right now. Oh, no, sorry. Yeah, so let's just go back to my starting point and keep on adding it to itself, right? So let's take an example. I have my starting point, and I keep on adding it to itself, right? A couple of times, let's say n times. I'm going to finish at an E point, okay? That's going to be my ending point. For example, if I go back here, my starting point would be the P right there, 10 will be the N, and then my ending point will be the 10P right here, okay? And another thing on elliptic curves is that division does not exist. So if I want to resolve this equation right here, my ending point equals n times my starting point, it's really, really difficult. So since division does not exist on elliptic curves, even with the E and the P given, it's really difficult to find the N. And this is actually where elliptic curves are really interesting because of that. Let's take an example right here of the curve for Bitcoin. So this curve is y power of 2 equals x power of 3 plus 7 modulo p. So where p is this prime number right here, it's kind of hard to see that it's a prime number, but it is. And so this is on a finite field. And basically, this curve right here is used for most cryptocurrencies, not only Bitcoin. And it's called SECP256K1, but you must think, how does she use this for Bitcoin? Like, how is it relevant for cryptocurrencies? Basically, why do we use elliptic curves for cryptocurrencies is for the trapdoor function. What does that mean? It means that if I give you a point A, like I give you something, you can easily obtain a point B. So going one way is pretty easy. But on the other way, if I give you B, it's really, really hard to retrace the way back to A. Yeah, it's really, really hard to retrace the way back to A, basically. And so if we go back to the discrete logarithm problem that we defined earlier, which means that because the division does not exist on the elliptic curve, it's really hard to find the n. And let's say, for example, right here, your E is your A and P is your B. Sorry. If we go back to that and we apply it to cryptocurrency, we have to define first what's a public key and a private key. Let's take, for example, that your public key, which is your ending point, are the x and y coordinates of the ending point on the elliptic curves. What is the public key? Is the address that you're going to give to someone when he wants to send you some cryptocurrency. But you know, it's not safe to give this kind of address, so it's related to your private key, which will be this n number, which is really, really hard to find. It's a random 256-bit integers. So basically, your private key is just the number of times you're going to add the base point to itself. And even having the function, the start point, and the end point, it's really, really practically impossible to find back the n. And this is why we use elliptic curves to secure information on elliptic curves. To give an example, so in cryptography, there is two main rules. The first one, it is that it is computationally practically impossible to derive the private key corresponding to a qubit public key, which is possible on elliptic curves as we just saw earlier. The second rule is that it is possible to prove that one knows the private key corresponding to a public key without revealing any useful information about the private key in the process. These two rules are able to obtain with elliptic curves, but also with other things. For example, RSA, which use prime numbers. This is what most of people use for now, RSA, because it's a little bit easier to use. But the main difference between those two is you're going to notice it. If I can just ask you a question, what is the main differences you look into those two pictures?
This space.
Sorry?
This space.
One is a tiny bit bigger.
Yeah, like one is a way bigger than the other one, right? And so the first one right here, this corresponds to a private key and public key created for RSA, and this right here with elliptic curves. These two keys have the same level of security, but as you can see, one is way longer than the other. That's why elliptic curves are used, because for the same level of security, you can have a way smaller key. As an example, for elliptic curves cryptography, for a 256 long key, you'll get for RSA 3072, which is a large difference. If you go higher, 384 in elliptic curves, it's 7680 for RSA. And this is considered right here by the government for the top secret level. So this is the level that you use to share top secret information. So yeah, basically this is all I needed to say about elliptic curves. They're not just a fascinating mathematical object, and the fact that it's really hard to derive something out of it has actually used in cryptocurrencies and also to secure information, transferring different type of private information. So they're indispensable for the security and efficiency of most cryptocurrencies. By enabling the secure public and private key generation, they ensure the trust and reliability of the blockchain. The beauty of elliptic curves lies in their duality because they're simple to use but really, really hard to reverse engineer, making them perfect for cryptographic application. Perfect. Thank you for listening.